Hello and welcome to this short introductory video series about machine learning. My name is Bojan, and the main goal of my work is to empower more people to take advantage of machine learning by making it more easy to use. In this video series, we try to cover the most important concepts and show how they fit together without going too much into details. If you're a beginner trying to make sense of the field of machine learning, we believe these videos could help you get started. Here's an outline of the topics we'll cover in this video series. Each topic is formulated as one particular question related to the field. In this video, we will focus on the third question. As a quick recap of the previous video, we went over the basic categorization of machine learning problems. We talked about two general categories: supervised learning and unsupervised learning. Supervised learning comprises of regression, which works with real-valued outputs, and classification, which works with categorical outputs, meaning a variable can take one value from a finite set of available values. We further divide it into binary and multi-class classification, depending on whether we have two or more categories. As for unsupervised learning, we mentioned clustering, which is about discovering groups in the data and assigning data points to those groups, and anomaly detection, which is about discovering patterns in the data and identifying data points that breach those patterns. What differentiates supervised learning is the fact that the training data contains a supervision signal. That is, for each input data point, it contains a correct output data point, which we call the label. In unsupervised learning, there is no such thing, and our methods have to discover patterns simply by observing input variables of the given data points. We now move on to the third question, where we will go over some concepts that are essential to making machine learning actually work. In this video, we will mostly focus on supervised learning. There are ways to generalize these concepts to unsupervised learning, but we will not cover them here. Let's go over the most basic supervised learning setting. In the very center of our interest is a component which we call the predictor. The predictor takes input data, which we call features. These can, for example, be images of handwritten digits. Given the input data, the predictor produces output data, or predictions, which can be assignments of handwritten digits to a category, which in this case can be a number between 0 and 9. As mentioned in previous videos, a classical approach would expect the predictor to be able to perform this task completely by itself. But as we saw, there is a missing piece of information that it needs to function. We call this piece of information the parameters, or weights. As the predictor produces its output predictions, in supervised learning, we can compare them to true predictions, which we call labels. We can use these labels to check how well a predictor does its job, for example, at correctly classifying these digits. To achieve that, we use an objective, which is a function that can compare the predicted class and the correct class in order to produce a score. This score allows us to quantify the quality of our predictor. For example, an objective can be accuracy, which is the proportion of correctly classified digits. And if it is, for example, 80%, then this can give us a feeling about how often we can expect the predictor to give us the right answer. Put simply, our main goal is to maximize the score of the objective, and the only thing that we are allowed to change are the parameters. Everything else, including the data, is a given. To achieve this goal, we need to be able to learn the parameters, which can maximize this score. Mathematically speaking, the predictor can be seen as a parameterized function, and by changing these parameters, we can change its behavior. We call this parameterized function a model. The objective is another function that is used to measure the goodness of the predictor by comparing its outputs with the true target outputs that are found in the data. The main question is, how do we go about choosing the best parameters to maximize the score? This is where the strong connection between machine learning and mathematics comes in. In mathematics, whenever we are talking about finding the best parameters that maximize some objective, we are actually talking about optimization. Of course, we won't go too much into details, but just for reference, we will show this very basic mathematical formula that defines an optimization problem. It has the following four components: the search space, which is essentially the set of all possible elements that we are searching over. Each member of this search space is what we call a candidate solution. The optimization problem is solved by selecting the candidate solution, which is in some sense the best, and proclaiming it to be the final solution. However, in order to be able to pick the best candidate, we have to be more rigorous. We need to be able to compare solutions to know which ones are better and which ones are worse. For this, we need the objective function, which can give us a real valued score for any candidate solution. An example optimization problem could be that we have two weights of our predictor, x and y, and we want to select the best weights to have the best accuracy score. In that case, the accuracy would be our objective function. The major challenge of optimization problems is that the search space, that is, the set of possible solutions, is usually enormous. As a result, it becomes impractical to check every possible solution. Therefore, we have to do something smarter. One such approach, commonly used in machine learning, is called gradient descent. In plain English, it just means going downhill one step at a time. Of course, there are other optimization methods. Gradient descent is just among the most popular ones. Now, we've mentioned that gradient descent means going downhill step by step. But let's expand that notion a little bit and see briefly how it works in the context of machine learning. Let's say we have a single parameter, w, to optimize based on some cost. A cost is simply the opposite of a score such as accuracy. It can be represented as the amount of error. So the lower the cost, the better, which means we need to minimize it. Those are just two sides of the same coin. We plot with a solid line the cost of every possible value of our parameter w. Our goal is to minimize the cost, but let's say that computing the cost of each possible value w we can choose is very expensive. So we cannot compute all of them, and we have to have some strategy. According to gradient descent, that strategy is to start from some initial point, which we can pick at random, and then just take a step either left or right. We make the choice simply based on which side takes us downhill. We then repeatedly take steps downhill until we have reached a point where there is no way to go more downhill. Then we know that we've arrived at the minimum point. We have chosen a single variable w only for simplicity, but our search space can have two dimensions, or as many dimensions as needed. A gradient is a mathematical concept, which is like an arrow that shows us the direction in which our plane is the steepest. A gradient needs to be computed somehow. Usually, it is not possible to compute it exactly, so we compute an estimate. We compute this estimate based on training data we have. Sometimes we can use the entire training dataset at once, but if the training dataset is too big, then the computation of the gradient itself can become very expensive. To overcome this, we can take random subsets of our training data to compute a rough estimate of the gradient. This is called stochastic gradient descent because of the randomness involved. Another flavor of gradient descent is called batch stochastic gradient descent, which not only computes the gradient at each step from a subset of the data, but to ensure that it covers all the data, it splits it randomly into chunks, which we call batches. Now, if we have, for example, 10 batches, and with each one, we're able to move 10 steps downhill. What happens if we need more steps? Then we go over the data again from the first batch and continue to make steps. Each time we go through all the batches of a dataset once, we call it an epoch. It's just important to note that it is quite common for hard machine learning problems that we will need to perform many epochs before we are able to find the best solution. That's all we have for this video. We hope it managed to clarify some basic concepts. Make sure to check out our next video where we try to dig deeper into the concept of a machine learning model. We're going to see what does a model do and what kinds of models exist. Finally, feel free to check out our website and learn about our very own effort to make it easier to use machine learning for your specific problem. You'll find all the links in the description.